Okay, this is the 12th and final video in this series dedicated to Bessey shuffle diagrams. And so here I thought we would review for the last time some definitions. A shuffle S is said to be a Bessey shuffle if and only if S preserves or inverts Bessey sequences. Recall the Bessey sequences of order 8 are 1 0 0 1 0 1 1 0 and its inversion 0 1 1 0 1 0 0 1. Also recall that we have a color coding scheme for the position values. Position values 1, 4, 6, 7 are color coded black, and position values 2, 3, 5, 8 are color coded red. This will enable us to detect whether the Bessey sequence has been preserved, as in the case here, or inverted, as in the case here. Recall, an inversion occurs if the cards that originally began in positions 1, 4, 6, and 7 get moved to positions 2, 3, 5, 8, and vice versa. Also, recall that the two Bessey sequences of order 8 can be characterized as follows. The top one here has the property that the ones are in positions 1, 4, 6, 7, and the zeros are in positions 2, 3, 5, 8. The inversion of this sequence is found below, and the relationship between the zeros and ones switch places. The first shuffle for today is shuffle 45, and it is a repeat LR shuffle. To derive the permutation representation for this shuffle, we begin with our ordered packet 1 through 8, and we perform the shuffle. The shuffle is performed as follows. It's an LR shuffle, so left, right, and then we perform that same set of actions to each half. So we'll do left, right for that half, and then left, right for that half. And now the stacking here is as follows. We're going to stack, now remember this is pile 1, 2, 3, 4. So pile 4 will be stacked on top of pile 2. Pile 3 will be stacked on top of pile 1. And then the right pile will be stacked on top of the left-hand pile. Okay, and we also call this a leapfrog stacking. So 4 leaps over 3 and lands on 2. Pile 3 leaps over 2 and lands on 1. And then from here, we're stacking the right pile on top of the left. So what is the new ordering that we obtain from that shuffle? Well, it's right here. 2, 6, 1, 5, 4, 8, 3, 7. So the Cauchy two-line notation for this permutation is as follows. The top row is always 1 through 8. The second row is 2, 6, 1, 5, 4, 8, 3, 7. Converting this to cycle notation, we obtain the following. 1 goes to 2, so we have an arrow from 1 to 2. 2 goes to 6, so there's an arrow from 2 to 6. 6 goes to 8, an arrow from 6 to 8. 8 goes to 7, an arrow from 8 to 7. 7 goes to 3, an arrow from 7 to 3. And finally 3 gets sent back to 1, so it cycles around, giving us a 6 cycle. The remaining values are as follows. 4 goes to 5, so we have an arrow from 4 to 5, and then 5 gets sent back to 4, so that completes a 2 cycle, also called a transposition. Color coding our digits, we obtain the following. Recall position values 1, 4, 6, 7 are color coded black, and position values 2, 3, 5, 8 are color coded red. This gives us the following. Black 1 gets sent to red 2, which is sent to black 6, which is sent to red 8, which is sent to black 7, which is sent to red 3, which wraps around and gets sent to black 1. Black 4 goes to red 5, which goes back to black 4. So we see that the following has occurred. Each value gets sent to a value of the opposite color. And when that happens, we say that inversion has occurred. And this simply means that everything that began originally in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8 in some assignment, and vice versa. So inversion has occurred. We can illustrate inversion by using our Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0. So it should be the case that after we perform this shuffle, we should get the inversion of that Bessey sequence. So let's go ahead and perform the shuffle. It's the repeat LR, so you go left, right, left, right, left, right, left, right. Perform those same actions for each half. Left, right, left, right. Left, right, left, right. Now we're going to stack the fourth pile on top of the second, the third pile on top of the first, and then we're going to stack the right pile on top of the left. And so we now should have the Bessey sequence 0, 1, 1, 0, 1, 0, 0, 1, which we do. Taking a look at the shuffle diagram, the top row on the left, we see that the following diagram represents this permutation. We see the 6th cycle, 1, 2, 6, 8, 7, 3. So it should be the case that if we begin at 1, there should be an arrow from 1 to 2, which there is, from 2 down to 6, there's an arrow, and there should be an arrow from 6 up to 8, and an arrow from 8 to 7, and an arrow from 7 to 3, and then we should have an arrow from 3 back up to 1, and we do. And that completes this 6th cycle. We also say that these 6 values constitute an orbit. For values 4 and 5, since they constitute a transposition, we would expect to see a double arrow between those 2 values, and we do. Those 2 values constitute their own smaller orbit.